Hi, I'm Ariel, and this is GigaPath, and I'm from Geo SRE in Google Sydney. So typically what we work on SRE level is like we make sure the system is reliable end-to-end, making sure that user doesn't see the errors on our problems that we have. We're not really that interested in saying reliability of individual component if they do not affect any end-to-end reliability at all. So the talk today that I have is safe client behavior, which is how do we ensure clients behave nicely so that we don't do bad things to our server. So why is clients important? Because clients' behavior is something that we can't really control. Service can't protect themselves really nicely from misbehaving clients. And despite how careful we have against like thinking, okay, if I code this is probably fine. There's so many layers of how humans and how people or clients interact that we can't account for, which means that this is a very hard problem and really easily that we can just bring a service down by doing something really badly and overloaded our server. And so let's start. So this is how typically the normal client-server architecture that we think in uni or something, where we have a client and talk to a server. But what is the case in real life? How many clients do we actually have? So Google, I think, announced last year that we have now 2 billion active Android devices. So that means we actually have 2 billion clients out in the wild that could affect that talk to our server. And the other question would be, in that case, do we have 2 billion servers on the other hand? That's not usually the case. We usually have like 20, or maybe 200, 2,000, or even 20,000. But regardless of the number, it seems like the number of clients to server is always way less than we have. So this is actually how the picture looks like. In real life, where we have the number of clients way outnumber the number of servers. So what safe client behavior essentially means is do not DDoS yourself. DDoS is distributed denial of service to your service. I don't think anyone who develops a client or service would intentionally trying to DOS themselves unless that's their aim. But as I said before, it's really hard to imagine how 100 million, say, clients outside would trying to act independently of each other and what their action collectively would do to our server. Bugs are really hard to spot on clients, especially like we have clients of different architecture, different, different CPU, even different platforms. And proper behavior is really hard to test. The other thing that makes this really hard is more like organization problem. Like typically maybe the client developers are not really the same person who develops the backend. They can be, but usually they are not because we specialize on different things. And that means that they have very different set of skills and they probably have different priorities, and maybe the client developers are not aware of the problems that the backends would face, which means we should probably have some better safeguards against how clients affect the server. So I guess this comes to the question, which requests are unsafe? Like what requests do we count as not safe and should probably be careful in this safe client behavior? One of the interesting things is that user-initiated requests usually not the problem. That's just so fast we can try to click on a mobile app or something. Like humans are not subject to Moore's law. Most of the time people just react, like click button, and so that's not as fast as, say, a machine could have been. The most dangerous requests are actually the requests that are not user-initiated. It could be like an app startup, like maybe the app startup will send off like gazillion requests to the server to get the state. It could be periodically syncing up the state of the app, or even retries. Retries that is not really well coded can actually cause more problems than you think. Then, what is the worst case that could happen if we don't have good client's behavior? So this is, I don't think that is actually a photo of a data center being caught on fire. This is just a photo that we got from Google search. They probably have fire alarms triggered due to overloaded server, but I don't think there's one that actually caught on fire due to server being overloaded. So typically, if we have the wrong client behavior, we would probably overload the server due to the request spikes coming in from retries or unintentional synchronization. And that is something that we aim to avoid in this talk. So we talk a lot about what's the worst that can happen. But what is the best that can happen? Like, what is the behavior that we want? So this is a request graph that looks like the blue line is the request graph, the user request. The red line is errors that we serve to the user. This is the perfect world where the user request pattern is smooth and we never serve any errors, no oscillation, no spikes. That's the best case that we could have happen. And so for the following slides, I would just imagine we have a mobile client app that, say, it checks the time every 5 minutes or so, for example, to see what the state of the data is. So rule number one for safe client behavior is if we can jitter them, we should jitter everything. And what does jitter mean? I think this is a definition that we got from dictionary. Jitter as a noun means it's the deviation from true periodicity of presumably periodic signal. But what does that really mean in the context that we want in safe client behavior? What we want is we want to add randomness into the periodicity of a periodic signal. What we want is adding randomness into the client request to us so that the patterns is no longer synchronized or accidentally synchronized. So remember I said we have a mobile app that talks to the server every 5 minutes. The most naive implementation that we can have is that while the app is on, send an RPC, and then wait for 5 minutes, and then send an RPC again. Can you imagine what the request graph would look like in this case? This is how it would look like. For when the user initialize the app, you have an initial spike, and then the service will be idle for the next 4 minutes until the 5th minute it sends request again. So this is probably the worst case that could happen. Your service is mostly idle most of the time, but you have to provision for the highest spike that you can get, which means you're wasting a lot of good resources. And I should also mention that this line doesn't have any axis labels because we are interested in the shape of the load, not the value of the load. So let's put some jitter in. Let's not retry exactly 5 minutes. Let's put some randomness into it. Let's say, let's retry, let's send the RPC and then retry between 2.5 minutes to 7.5 minutes, which means that the expected value of the period is still 5 minutes, but the actual times varies. And this period is random based on every execution. And this is how the graph will look like. We'll have the initial spike because we haven't jittered that. And subsequently, after the first initial request coming in, everyone would just kind of have the sending RPC from between 2.5 minutes to 7.5 minutes, which means we no longer have synchronized spikes. So is the synchronized startup a problem? We can say that not a lot of people will start the app at the same time, right? But I think this is actually a problem because not a lot the requests that we care about are mostly backgrounds and whatnot. And for example, you can have apps saying, hey, when it's 4 a.m. user time, do this other thing, or when the app is start up at a certain time, turn it back on again. And so if, say you say 4 a.m., everyone's phone at 4 a.m., whatever the local time zone is, would just spike up the load, which means we should actually care about the synchronous startup time. So that's another thing that we can jitter, and the rules was jitter everything, is that we should also synchronize jitter when we start sending the request by doing the same thing again. And how would the graph look like now? Ta-da! This looks so much better. We no longer have the bad huge spike in the beginning, and the load looks smaller and smoother. But there are still some oscillation at the start. You can see this load spike is actually higher than subsequently. So where does the load oscillation come from? And can we avoid that? So remember we jittered the period. And so in the graph over there, the overlapping period actually leads to oscillation at the beginning. So every of the different color line is the probability of the request getting sent at the time, and all this period overlap to each other will produce the blue line that we see for the request. So eventually, enough of them overlap to smooth things out. So we have the initial oscillation, and then subsequently, the longer the time runs, the more of them overlap, and now we have a smoother graph. This is usually good enough since oscillations are quite limited, and also inadvertent synchronization is quite rare to begin with. But can we do better? So this is if we truncate the epoch to the nearest multiple of the period and then add the random delay. So we actually add jitter to the resync period instead of the execution period instead of the resync period. And how would the graph look like then? Because this is really boring. We actually get to the first graph that we wanted, really smooth load profile, we don't have spikes, no oscillation. So why don't we do this often? So look at this statement. You have the code that truncates the execution time to the nearest epoch, and then add randomness to that. What happens if you switch the two lines around? So the answer is you add the randomness, and then you throw away and then you truncate it to the nearest epoch, which means you throw away all the randomness and accidentally synchronize all your retries on the same time. And so that's how the graph will look like. That's not what we want. And it's a very, very simple bug to make, and it's really quite hard to debug because it's 2 lines of code that just swap the order around. And I do not know how we would actually test for this. Rule number 2 of safe client behavior would be don't retry. Terms and conditions apply, because some retries might be good. So right now, the RPC frameworks actually makes it really easy for us to do retry. We can just say retry 3 times or retry indefinitely if we want. And this is really attractive for engineers because retries improve reliability when our backends are just being unreliable or we have network issue, right? Retrying would just mask the errors away. But we really need to think carefully when we do retries, and the default should be don't retry if we can. So let's go back to our code, and we have a very naive retry algorithm, which is like if we get an error, we retry every 10 seconds, and once you succeeded, you wait for 5 minutes. Guess what would happen? We would have a huge spike of error rate, And then because we did not add jitter after the retry finishes, it inevitably leads to synchronization. Why is it so? Because you retry every 10 seconds, and then the server affects every client around the same time, and every client will see the outage in the server at the same time, which means that the client will retry, get error until when the server recovers, all clients recover, and now everything just behaves the same again. So what should we do here? We need jitter. We add jitter to the period that we, now let's add jitter to once we finish retrying, and then add more jitter as we introduced earlier on. And this is how the graph will look like. We still have the initial error spike when the server is having issue, but you can see that we no longer have the synchronization problem that we had in the previous slides. But the rule was jitter everything. And there's another thing in here that we haven't jitter, and maybe that would help with the huge spike of errors in the beginning. Can we retry, can we jitter the retry delay and not retry the periodicity of the thing? Like, say, if we have an error, we retry between 5 seconds and 15 seconds. Would that help? Like, can we just use that and not bother jittering the wait period? The answer is no. It doesn't help as much. We definitely need to jitter the periodicity too. The third rule, since some of us like retry, and retries sometimes are good, we should back off when we do retry. We should not retry every 10 seconds or so. So this is the graph that we're looking at. And why do we want back off, say, in our request? Because errors, server errors that we send out can mean a lot of things. One of the errors could mean we are out of quota, which means your client are being rejected because they don't have any more quota that the server's like, no, you don't have enough quota, get away. If you retry on out of quota error, that's not gonna solve the problem that you have. Your request will reach the server and the server will be like, but you are out of quota, go away. And so if you have a really dumb retry logic and retries on out of quota, it's just overloading the server by just go away. Like the server just be like, you're out of quota. So the solution to the out of quota and retries problem is that you probably want to do like, give the client temporary more quota, but that's not a good business model. And if you really do give them more quota, you should also tell them, hey, can you fix your retry error bug? And also not retry on quota, out of quota error is not going to be helpful. So the backoff that we talk about is exponential backoff. Exponential backoff is the way that we kind of phrase out the backoff periods that we have by adding progressively longer wait time between consecutive errors response. If we do that, then we will have a request and error graph that looks like this. We can see that there's an initial spike, but then it kind of the subsequent spikes are less severe, and it's kind of get this smooth out. This is kind of the pattern that we like because the graph is no longer just a spiky thing. But the thing that we don't like about this is that it's okay, like it's a good graph looking, but it's kind of blockiness. You can have like retry error spike per block, and that is pretty annoying and something that we can probably do better. So one thing that we can do better is just adding more jitter. Adding jitter would just even out the request or the retries, and that means that we could have a smoother profile at the end. This is what we would have if we add jitter. We have a more smoothly dropping request rate, you can see. It's the same I guess same patterns from the previous graph, but then you can see the error rate graph is actually much smoother. It's not blocky anymore. But there's one problem here. You can see that the request rates continue to go down because the blue line at the beginning and the blue line at the end, once the server outage is over, the blue line doesn't really recover back to the previous state. That's because some of the requests just ended up in retries, and because of the exponential backoff, it actually takes them longer to contact your server. This means that some clients probably wait longer than it needed to be, or wait much longer than the intended periodicity. So this means we should probably cap how long the client does this retry. So we can just do something really easy like retry 3 times and give up and then just wait for the next RPC. Or we can be like, as long as the delay that we introduce is less than, say, 5 minutes in this case, we can still retry, but once it's longer, we just drop the request and just forget about the RPC and issue a new one. Or we can do like 2 times the period if we think that the server is really, really hammered or something. And then we will have a better graph looking where we have the rate spike and then the server recover, and then you can see the request pattern, the retries kind of get capped, and we're no longer having outage that is longer than necessary. So here are the retries terms and conditions. One of them is, if we can, don't retry by default. And if we do retry, please back off on the retries and select the retries behavior that you want based on the error codes that we receive. Don't retry on client errors. For example, if you send a bad request to the server, retrying that bad request would just have the server keep telling you, this is bad, I can't serve this, this request is bad, and it just keep repeating itself, it's not gonna resolve itself. Retry on network error, because that might just be network being flakiness. Timeout is very interesting because you could have gotten a timeout because your request is too big for the server to handle, or the timeout might just be the packet got lost somewhere along the line or something. So that you can retry that, but be careful because you might actually accidentally harm your server if you send a bad request or a very expensive request to your server. So far, we have talked about when we have a complete outage of the server. So what are the effects that we have during partial failures? So this is the basic, where we don't have jitter, we retries, and if we have a 25% error rate, then we can see that we have a gigantic spike of errors, and the spike doesn't subside, it just stabilizes at a high level. That is probably not what we want. So what if we introduce some jitter? You can see that the error, what happens if we, say, exponentially back off? You can see that the errors actually go down over time, but we can also see that the little spike of errors that we have, those are like the power of 2 apart, because those are the retries back off, because we use exponential back off without jitter, which means that at the 10-second point, 20-second point, we'll have spikes that looks just like that. So we really do need the jitter that we have so that we can smooth out the load profile, and that's how it looks like if we have jitter, exponential back off, and everything. The other thing that we should do is move control to the server. Why? We have, as I guess mentioned before, the number of servers that we have is way fewer than the number of clients, which means that if we move the control to the server, we have less things to be controlling, or like less things to update. And the other thing is that server is something that we have control over. It's harder to control the client. It's harder to get people to update their app than to, say, switch a flag on your server. And the bugs are easier to fix because we actually directly have control over the server. there's actually not a lot of standard in this area other than the fact that we have a retry after header that the server can set being like, hey, come back in 5 minutes time and whatnot. But that doesn't mean that we should just, move the control completely to the server and doesn't have good client behavior on the client side. We should always have that is because what if the request never got to the server because of the server being overloaded? The server has no way of telling the client come back in 5 minutes time if it never has the chance to process that request, right? So safe client behavior still applies on the client side as well. And the things that we can control on the server side can be, we can control how long, say, the retry should be. Like if we think that we're gonna have a really long outage, tell the server to come back, tell the client to come back longer than normal. We can tune that, and obviously we should add jitter to that, otherwise you'll just introduce synchronization again. The other thing that is really useful is move, or like, because we have all these requests coming in. It might be one server serving gazillion different type of requests. One thing that would be really, really helpful, especially if we want to move the control to the server, is that we should tell the server what type of request that is, like expose as many information as you can to the server so that we can actually prioritize or determine how we would behave depending on which type of request. For example, if you know that this request is going to trigger a retry storm, we should probably serve that request and not drop it to the ground, because if we drop it, then we just have like 10,000 requests coming in. That's probably something that we want to avoid. And we can also, because the information, if we tell the server this is a background request versus a user-initiated request, we can actually prioritize and say, okay, I'm overloaded, sort of, and I want to prioritize serving user requests because user is waiting for it. The background app updates thing can probably be dropped to the ground because they will either retry, or it doesn't matter if it takes them 10 minutes to finish the request versus 1 second or something. So then all the client's behavior we talked about before applies more towards like mobile devices to server requests. And we have a new architecture out there that's microservices. They are actually slightly different to how mobile clients talk to the server, because in the mobile device world, the mobile client acts independently of each other and they don't really have a good view on the state of the server. But if you are in the microservices environment, it's probably different, because you probably have an individual client. A microservice might send a lot of requests to that one backend and might know a little bit more about the state of the server. Microservices is like the new architecture style of developing application. It's just like breaking down big monolithic application into smaller parts, and every part of them have its own realm of responsibility. So because the microservices has a state of its backends, it actually knows what kind of request it sends to the backends and how the backend state is right now. We should have probably retry budget. Retry budget is really useful for microservices because we kind of want to avoid the situation where we send gazillion requests to the server, but then most of the requests are, say, 90% retries. We should monitor the retry request and probably let some percentage of it through so that we don't overload the local backend. And the other thing that is, I guess, new and upcoming, and there's a link here for the SRE book that we published a while ago that's talked about adaptive throttling. It's like, because we know how our backend performs and the state of the backend, whether they are overloaded and whatnot, we can use that information and decide whether we would send the request and whatnot. If, for example, we send the request to the server and we notice that every 10% of our requests always failing, we might as well decide, hey, every time I send those requests and 10% always fail, we might as well not send that 10%. Why do we not want to send the 10%? Even though, say, we drop the request or just deny the request, it's actually a load on the server. We might as well, on the client side, behave and be like, let's not even try to overload the server when it's already overloaded by just not sending the 10%. And so that's one good way of you protecting your backends, if you have the knowledge and information about your backends and able to determine it. So summary over the entire talk is that we should jitter everything. Don't retry if you can. If you retry, back off. Don't always retry at the same time. Move control to the server. Expose information to the server that would help them debugging. Use retry budgets in the microservices role, and use adaptive throttling if you can. The other thing is, I should add a reminder, is pick the requests that you do for retries, because retrying on client errors and out of quota errors will not help the server or your service as well, your client as well. Any questions?